All right, what's up everyone? Welcome back to Structurefree Office Hours. And in this video, we are meeting to do an example problem with biaxial bending or an unsymmetric bending problem. And here, the unsymmetric bending equation, it really, because you have bending about two axes on the cross section, this normal stress is this negative mz y over iz plus my, a distance z over iy, right here. And so you can tell already we're going to have to calculate moments of inertia about the z and the y axes of the cross section, as well as, even before that, determine the neutral axis location, or at least the centroid, the geometric centroid. And here I have this T shape. I know that I have one line of symmetry up and down the middle, and my centroid will lie somewhere here. And so I want to find this distance. I want to find the distance to the neutral axis. It's all good. Right here, this will be my neutral axis. So one of the first things I want to do is I'll just go ahead and look at the geometric properties. But I have this cross section. I have a 2 kilonewton meter moment that's actually pointing like this. It's, I believe, like this. And did it have an angle?
Yeah, 60 degrees.
Oh, 60 degrees. So here, the moment is actually here on the face of the cross section, like this, right here. And so I put my thumb in the double-headed arrow direction. This upward direction would represent plus y, and this direction would be plus z, and then coming out of the page would be the x-axis, and this is the moment that's being applied on the cross section. So one thing I want to do is find the centroid, this location here. In particular, I would like this distance from, let's say, either the bottom or the top. I'll choose my bottom as a reference, so I'll call that y bar. All right, so one of the first things we're going to do is determine some geometric properties. All right, so for this, I already know, at least I know where it is in terms of left to right, but up and down, I'm trying to find y bar. Y bar is the sum of ai yi over the sum of a, the first moment of area. And here I would break this up into two elements. I might call this one element 1, and I'll call this one element 2. And now I'm just going to follow this pattern of base times height. So 200 times 50. Yi is the distance from the reference, which is down here. This is my reference, to the center of the element, which would be right here. Here's the center of the element. So that is 200 plus 25. So it's 225 millimeters. Plus the area of the other element, area 2, which is base times height 50 times 200. And the center of this element from the reference is 100 millimeters divided by the total area. So that's 200 times 50 plus 50 times 200. And then when I calculate this out, my friend is telling me that I have 162.5 millimeters. Yay. All right, that seems reasonable. Yeah? That seems reasonable. Okay, so 162.5 millimeters. So I have that. Now I want to, because I know, at least in this relationship, I have to determine IZ and IY, right? IZ and IY. And so here, as part of my geometric properties again, continued, I want to calculate my moments of inertia about the z-axis. So with respect to the z-axis, that would be as if I'm resisting rotation about the z, right here. So this is what we've calculated in the past with just our my over I formula. This is the bending that we're used to, okay? And so here, IZ is the sum of IZI plus AI dyi squared. And it's dy because the distances are in the y direction, right? The distance from the neutral axis to the center of each element. And so here, this would be, so for instance, area 1, I'm taking moments of inertia about its horizontal axis. So that would be 1/12 times 200 times 50 cubed, plus the area of that, which is 200 times 50. And then dy is really the distance from, dy is the distance from the center here to this right here. So this would be dy1, the center of the element, the distance from to the center of the element from the neutral axis, which really, if I, is just 225 minus 162.5. And we want to make sure that we remember to square that quantity right here. Then the second element will be plus 1/12 the base, which is 50, times 200 cubed, plus 50 times 200, and then the distance from the reference, from the center, distance to the center of element 2 from the neutral axis is just 100 minus 162.5. And again, and now if I go through and I calculate some numbers, IZ would be, what would it be? Let's do some calculations. Two 2.083 times 10 to the 6 plus that's the total that you got? Okay. Let me pause this.
Well, I got 11 million.
11. Oh, okay, yeah. So I got 113.54 times 10 to the 6. So maybe we're off by a factor. Okay.
113.54 times 10 to the 6.
Yeah.
I had to say
Okay. Millimeters to the 4th. So that's moments of inertia about the z. Right here. That's the moment of inertia about the z. Now I want to find the moment of inertia about the y-axis. Okay. So about the y-axis, one way to look at this is as if I turn this thing to the side. I think for some students this is easier to see. Like if I turn it to the side and I go like this, and then the y-axis would be this thing right here, right? And now basically what we're saying here is that when I do 1/12 base times height, the base is always parallel to the axis of like rotation. Yeah?
I see it.
The axis, right? So here for IY, I'll use a different color. I'll put it in blue. IY, like I could call this element 1. I think is that what I called it before? Yeah, element 1 and element 2 here. But here, IY now would be 1/12. The base would be 50. And the height is 200 cubed. And then I could do a dy squared. But look at the neutral, if you will, the centroid line is here. The centroid of 1 is there's no distance. Does that make sense? dz would be 0.
Oh yeah, I see.
Yeah, plus, so it'd be plus 0 plus 1/12 the base of 2, which is 200 times 50 cubed. Oops. 50 cubed plus again 0 because there's no distance from the center of the element to the neutral axis, or the axis of rotation at least. Okay. And this is, oh, actually we already kind of calculated this. It would be 2.083 plus 33.333. Let's see.
35.42.
35.42 times 10 to the 6 millimeters to the 4th. Okay, so that almost feels like all the hard work right there with the geometric properties. So when I go back to this thing right here, I've calculated IZ and IY, right? So it's not that difficult. It's just tedious.
Yeah.
Yeah, and then moments about the Z. right here. So here I have this moment. This angle right here is 60 degrees right there. So if all it is now, if I look at the moments, I'm just gonna, break down the moments into components. So here, my moment vector, moment components, and these moment components, I have the vector m has a magnitude of 2 kilonewton meters and is pointing at an angle of 60 degrees like this, right? And so here mz, it's actually moving it's in the positive z. This was plus z and this was plus y like this. So mz is 2 kilonewton meters. Cosine of 60 is positive because that z component is to the left, and then my is 2 kilonewton meters. Sine of 60. That's it. And sine, is it cosine 60 is a half? Yeah. So this would just be 1 kilonewton meter, and this would be square root of 3 kilonewton meter. Okay. All right. So I have the moment component. So if I go back here, I have the moment components. So now the question is, which point on the cross section should I look at to determine my largest normal stress, right?
I would say the top.
Okay, so probably one of the corners, maybe one of the corners, okay? And I guess this one is kind of challenging because, the way that we looked at the largest normal stress due to bending was the furthest distance from the neutral axis.
Yeah.
Right? And here, because we have this unsymmetric bending, we don't know the orientation of the neutral axis. So it usually helps to look and find the orientation of the neutral axis so that I can at least get a sense of what's the furthest point from the neutral axis. So here, 1, 2, 3, 4, the neutral axis orientation. Now, it was this relationship was derived based on setting this equation equal to 0 and then looking at the ratio y over z.
Okay.
Does that, I don't know if that rings a bell at all.
Sort
okay.
of.
All right. And what it was, I think it was, we're going to have to double check this, but it was tangent alpha is tangent theta. I want to say it was IZ over IY, but I could be wrong. Let's see. And it's an equation that would be provided, right? It's on the inside cover of a textbook. It's in your fundamentals of engineering. Is it? I wonder if it's in the FE. Oh yeah, tangent alpha is IZ over IY times tangent theta. Okay, all right. And it's the neutral axis is where the normal stress equals 0, right?
Yeah.
Okay. So here, and in this, and another thing to remember was that positive theta and positive alpha. Here, if this is my z direction and this is my y direction, the positive angle was going this way. This was considered positive, like theta and positive alpha. Yeah. Okay. From z towards the y.
I can agree with that.
Okay. Yeah. And then and so now it's just alpha is the angle of the neutral axis. So here I would have, tangent alpha is equal to tangent of 60 degrees times IZ over IY, which we already calculated. IZ is 113.54 times 10 to the 6 divided by IY, which was 35.42 times 10 to the 6, and then the units would cancel itself out, and then I'm going to have to calculate alpha here. Let me pause this. And then we get 10 alpha is 5.552. I take the inverse tangent of that. Hopefully my calculator is in degree mode, and alpha is 79.6 79 degrees or 79.8 degrees. And so when I look at this thing right here, if this was 60, oh, this drawing's gonna get messy. What color can I use for the neutral axis? Do I have another color? No, I don't. Let's go with like blue. So here was 60 and then 70. This is the neutral axis. Yeah? That would be the neutral axis.
Yeah.
All right. And here this is the NA, and this angle right here in blue, man, this drawing is crazy. But this angle right here is at 79.8 degrees. All right. All right. And so now I look at this and I have to kind of look and say, what would be the furthest, I don't know if my drawing is enough to scale, but the way I do it, and this is, I guess, a rule of thumb that I like to think of, but it's like the furthest perpendicular distance from here would, I think, typically yields the largest stress, right? The other thing we have to consider is that, like, well, as long as, like, do I have a zone where I have, like, compression due to Z and tension due to Y, which kind of cancels out stresses, right?
Yeah.
And gets it closer. So the closer I get to the neutral axis, I guess the more zero I get, right? The more zero I would get. So it looks like
Top right.
the top right is definitely a candidate, and then maybe even this one here, right? And so let's look at, we'll call this point A, okay? So the normal stress, the coordinates of this, if I look at point A right here, the coordinates are like, let's see, the Y coordinate would be, Y bar was 162.5. So this distance right here is 250 minus 162.5 is 87.5, and then this distance is 100. So the coordinates of this, the YZ coordinate would be 87.5 comma 100. Yeah. And did I make a mistake?
Maybe with the 100.
Yeah, that Z coordinate. What should be wrong with that? What's wrong with that?
It's not 100.
It's not positive 100 because positive Z is to the left, so the Z coordinate should be negative 100. Yep, right there. It should be negative 100. So this would be my Y at A and my Z at A. And so if I look at this, if I calculate the stress at A, stress at A, I would say, we said Y A Z A is equal to 87.5 millimeters and negative 100 millimeters. And so sigma at A is this negative 1 kilonewton meter, the MZ, times Y, which is 87.5 millimeters, divided by the moment of inertia about the Z, which was 113.54 times 10 to the 6 millimeters to the fourth, okay, plus square root of 3 kilonewton meters times negative 100, the Z distance, divided by IY, which was 35.42 times 10 to the 6 millimeters to the fourth. Okay, I'm going to have to do a unit conversion. Otherwise, right, the meters I want to convert to millimeters or vice, but I think meters to millimeters would be more convenient here. So I would have like 1,000 millimeters per meter, and then 1,000 millimeters per meter. And now I can calculate this. I want to calculate this. All right, I hope I hit record. Okay. All right, so after some calculations of those parts, I get sigma A. If I add those two together, I get negative 0.00566 kilonewtons per millimeter squared, which is negative 0.00566 gigapascals, which is negative 5.66 megapascals. And that's my normal stress at A. Okay. And then the question asks for to find the maximum stress. So I guess you could check another point if you wanted to. This point here, I'll call it point B. And you can determine on your own. I'll let you figure out the coordinates for point B, and then you can, maybe if you're not sure if B is less than A, you probably want to calculate the stress there and see if it is. All right, let you check that on your own. All right, take it easy. Structure free.